Welcome to yet another science podcast, a podcast devoted to conversations with scholars containing philosophical, historical, motivational, conceptual, and technical questions relating to their research.
So one of the coolest things about programming is it has this ability to automate things. And when you first learn it, it's a fun exercise to find ways to automate little tasks that seem tedious. And when you first study programming, I think almost everybody wonders this eventually. What if you could get a computer to program itself? And recently, there's been a lot of media coverage on this. In particular, there's this GitHub Copilot technology that came out, and it's leveraging machine learning techniques to automatically program. And it's still a young technology, and it's not always sound. It's not always correct. But there's a whole other side to this. This has been thought about for a while, and we also have symbolic techniques. So what is autonomous programming? What is program synthesis? Are we close to automating away the programmer? And should a young computer science student be worried that they might not have a job?
Well, I think when we think about these things, it's useful to put a little bit of historical perspective, right? So, going all the way back to Alan Turing, there's this quote from him that I really like that talks about how programming will never be boring. Because as soon as some aspect of programming becomes boring, then we can just automate it and focus on the not so boring stuff, right? And, even if you go back to Fortran, right? When Fortran came out, it was the Fortran automatic programming system, right? And the idea was that now that we have Fortran, we don't have to program anymore, right? The machine is able to write the code that people today write by hand from this very high level notation, and it's not going to make mistakes. You're not going to have bugs. And, now we hear about that and it seems kind of laughable, right? Because now we think of that as this really low level form of programming, right? Writing code in Fortran. But if you compare it with what was there before, it sure was a huge step in automation. And if you look at the kind of bugs that you make when you're writing assembly, where, I forgot that, this thing was in this register, and I forgot what to save the value from this register into memory before I use it for something else, right? Once you move to a higher level language, you don't make those mistakes, but it doesn't mean that bugs become a thing of the past. You just make new mistakes, commensurate with the complexity of the things that now you're getting to try out. And so when you talk about bringing more automation into programming, at one level, it is part of this continuum where we're constantly trying to make programming higher level, more automatic. It expands the set of things that we can actually implement. And the amount of effort that is needed to implement them is reduced. But it also just means that now we become more ambitious, right? We're no longer happy writing, simple applications that run by themselves on the desktop, right? Nowadays, every application has, a multi-tier cloud distributed element, and it runs on mobile, and it runs on the browser, and it's graphical, and it's interactive, right? And we can do that because we have programming and an underlying systems infrastructure that makes all of that possible. So I I don't think we're in danger of all of a sudden running out of things to program because the machine programmed everything that needed to be programmed. But I think one of the questions that for us is super interesting is, how does programming change, given that we have a lot of these new capabilities? One of the things that is different about this new crop of programming technologies that you're seeing today around program synthesis is that they operate in a very different way from the ways we have traditionally automated things in programming, right? I think the big story of improving programmer productivity, I would say, in the last 13 years has been all about allowing people to hide and reuse, right? It's all about hide and reuse. Make it so that complicated things can be encapsulated behind really simple interfaces and then reused very, very easily, right? And that's what allows you to write, fairly sophisticated applications with very little code. The fact that we've now been able to build this enormous ecosystems of things that we can leverage that have this accumulated knowledge of enormous amounts of person years behind them. This new technology is a little bit different in that it's not about helping you hide and reuse things that you know how to do. It's there is a certain amount of reuse, and that many of these tools are learning from code that exists, and they're getting their knowledge from code that other people have written. But it's very much not hiding these in a sense. It's exposing it, right, and it's helping you write the code directly. And I think that raises some questions. Are we going to repeat all the problems with just copying and pasting code all over the place, right? Are we just taking bad, vulnerable code and putting it in everybody's fingertips? And so I think it raises a very different set of issues from what we're used to dealing with and the traditional ways that we're used to improving programmer productivity. So I think those are questions that we don't yet have very clear answers.
It's interesting because the technology comes from almost two different trains of thought, right? When you look at, for example, the Copilot technology, it's able to produce PyTorch code that looks like a grad student should be able to write, or it looks maybe even intimidating for a grad student sometimes. But if you think about the way it works, it's trained based off of several examples, right? And it's not always correct. On contrast, there's this other side of building these autonomous systems based off of deduction and reasoning. It's interesting because this problem, it's difficult to find a problem where we can apply these two ideas, these sort of abductive and inductive reasoning techniques with these sort of deductive techniques. Why is this such an appealing problem to be able to do this?
I think, to me, the big opportunity with this kind of techniques is to have systems that a little bit more closely mimic how people approach programming problems, right? If I ask you to code something, right, I give you a little description of an application that I want you to write. Generally, there's an initial stage which is almost muscle memory, right? It's building on your implicit knowledge, where you hear about aspects of the problem and you just know that, oh yeah, I'm totally going to need a graph, and this is really a graph partitioning problem. And just from hearing about the problem, you have a pretty good idea of how you should decompose it into subproblems, how you should organize it into code. A lot of that comes from experience, and you can write a lot of code, huge volumes of code, in almost this stream of consciousness mode. You're just typing and the code comes out, and you can write, sometimes a couple thousand of lines of code in one sitting.
Yeah.
That code never works, right? It's always the first step of the process. And I feel like that is the kind of process that some of these tools based on language models are kind of mimicking, right? They understand how code looks like. They understand these relationships between aspects of the specification and aspects of the code. And they're able to pump out large chunks of code all at once. But, just as in humans, generally that code that you get on that first sitting, where you're just going and writing, it never actually works, right? There's always a little bug. There's always, something you missed. And then often we rely on a combination of tools, everything from, the type checker is telling me that this doesn't type check. And based on that, I have some idea of how to fix this kind of type error or that kind of type error. A lot of it comes from you run it and you see that it's not doing what you think it's doing. And now you're thinking more deductively, okay, what do I expect the state to be at this point, right? Oh, it's not what I was thinking. Well, what I know about this particular API, what does it assume of its inputs, right? Maybe I should go and reread the documentation to make sure that I'm using it correctly, right? And am I passing the thing that I think I'm passing? And generally, this stage involves much more deductive reasoning, involves much more, stepping through the code and reasoning about exactly what each statement is going to do. It really involves this very precise, detailed reasoning, much closer to the sort of things that our deductive tools are able to do. And I think one of the big research questions today is when we're trying to automate this process of generating code, how do we get a good synergy between the capabilities of our program analysis / verification / reasoning, logic reasoning tools and our learning-based models? And how do we get the two of them to build on each other, to leverage the things that we're able to reason about through semantic reasoning versus the things, the kind of patterns and correlations that the neural models are able to capture.
I really like the way you think about it. The machine learning, the abductive part, the inductive part, it's used for sort of prototyping the code, trying to figure out what was done before, like what the solution will probably look like, getting something laid out. And then the deductive part is testing, making sure it's correct, getting everything bit precise. That was really quite elegant, the way you put that. This idea of combining these sort of two corners of AI. We have the symbolic side, the deductive side, and we have the pattern recognition and the machine learning side, the abductive and inductive side. Another area you work on is neurosymbolic computing. What is neurosymbolic computing?
So we actually started in this path when thinking about the problem of program synthesis, right? And how do we combine learning-based techniques and neural techniques with this kind of logic reasoning techniques? And what we realized is that there are many other settings, even settings that normally you wouldn't think of as settings where program synthesis would be the right tool or the right solution, where you're simply trying to learn something. Maybe you're trying to learn a model of the environment. Maybe you're trying to learn even a simple classifier for something. But where having a representation that involves some symbolic elements that allows you to capture, for example, prior knowledge in the form of symbols can actually give you a lot of benefits that you don't get from the purely neural learning approaches. And so we've been doing a lot of work looking at using these combinations of program synthesis with machine learning in order to learn either in context where you don't have a lot of data And so you're having to make very aggressive generalizations from small amounts of data, but you have a lot of prior knowledge that can help you constrain the space of solutions that you want to consider and help you generalize better. Also in situations where you really care about interpretability. Now, interpretability is one of these terms that can be a little bit fuzzy and can sometimes mean different things to different people. But in this context, often what it means is that you want to be able to have meaningful intermediate results, intermediate values in the model that you generate, that you're interested not just in the end-to-end behavior, but also in what happens in the middle and being able to relate it to things that you know about, let's say, the process that you're trying to model, so that you can better understand what it is that the system is learning. Sometimes it's very important to actually be able to provide guarantees about the artifacts that you learn. And what we find is that having models that have more symbolic structure can often make them much easier to verify and allow you to actually give strong guarantees about what this model is going to do. So this is, I think this is a pretty early stage for this research area, but it's pretty exciting, the sorts of things that we can do to leverage this combination of more optimization-based learning with symbolic reasoning.
When you look at, like, say, how a neural network works, it finds this representation of its input, almost like a mental representation of an input. It's this like real valued vector, and it's difficult to go from these real valued vectors to like a symbolic representation. It's such an important problem, right? To combine these two corners of AI, but it's so difficult, right? Can you speak to this?
Well, I think there's many different dimensions of these difficulty. One comes from the continuous versus discrete aspect of it. I think one of the big enablers for the deep learning revolution is that we discovered how to use massive amounts of compute available in the form of first GPUs and now even TPUs to be able to solve fairly complex search and optimization problems. We don't really have an equivalent to that in the discrete world. It turns out there has been a revolution around SAT solving in particular. For example, we do have the ability to solve logic reasoning problems at a scale that was completely unthinkable before modern SAT solvers came of age in the mid-2000s. And that gave us actually a pretty big lever, but we're still nowhere near being able to solve complex combinatorial problems at the scale that we can solve these continuous optimization problems. And in particular, we don't yet know how to leverage hardware quite in the same way. And so as soon as you're trying to solve for something that involves combined numerical and symbolic reasoning, the symbolic part can very quickly become a bottleneck. We just don't know how to do it as fast and at the same scale. So that's one. That's, I think, one very important limiting factor in how we're able to get the two kinds of techniques to work together.
Taking a step back, how did you find this problem? When you're a young grad student, there's so many problems to get attracted to. What was it about autonomous programming, program synthesis, that just got you so excited?
So when I started as a graduate student, I started out working in high-performance computing. And at the time, there DARPA had recently launched a new program to develop the next generation of high-performance computing languages. And
what were they?
Out of this program came, for example, there was a language called Chapel. There was a language called Fortress. At Berkeley, there was a lot of excitement around UPC, for example, and there was another language called Titanium. In general, there was this notion that we could develop these very high-level languages to program this very large-scale supercomputers. There was this language also that I was involved in at IBM called X10. And a lot of these languages, at one level, they were very cool languages. They were able to abstract away a lot of the complexity of writing high-performance computing code for distributed platforms. But at another level, even with all the facilities that you had in these languages, if you wanted to write really, really fast code, it was still very hard. And part of that was just this inherent problem that there was this big gap between the level of abstraction at which you'd like to describe some of these problems and all the low-level knowledge about high-performance implementation that goes into making a really, really fast implementation. And so this was sort of my frame of mind when I started to work with who then became my advisor, Raz Bodig, who was also really interested in sort of this question of, can we do better? Can we do something different? And this is where we started to think about high performance programming in a different way, right? What if instead of the magical compiler that we, you just give it the high level program and automatically figures out how to make it really, really run really, really fast on some underlying machine through, just applying compiler transformations and compiler optimizations. What if instead we had tools that allow users to first specify their intent at a very high level and then separately provide some information about how you want this implementation to look like. And rather than have the machine try to just come up with the implementation by itself, have the machine simply help you with, particularly tricky low-level aspects of making this implementation work. And I think that was sort of the big leap in going from thinking about this as a compiler problem, right? How do we go and optimize a piece of code, to thinking about it as a synthesis problem. How do we generate a piece of code that matches some specification, that matches some constraints given by the user, and that respects what the user tells you that they want this code to do, but that also searches very aggressively for low-level details. And so this is really how this whole work, first around sketching and then more broadly around synthesis, came about.
It's a very appropriate name. You're almost sketching in sort of the missing part of the code that you need. When did this problem of program synthesis get first proposed?
Before I answer that, a funny story about the name, what we were thinking about what to call it. One of the candidate names was skeletoning. And,
could you spell it? Sorry, skeletoni?
Yeah, like skeleton, but
I see. What the?
But we had the good sense of saying, no, that name sounds awful. Sketching sounds much better. So it was almost called skeletoning. But yeah, so sorry. So what was the question?
The idea of program synthesis. Where did it come from? Who thought of it first?
Well, I mean, the idea is pretty old. There were the seminal papers in the very, very early 80s from Waldinger and Mana, there was this very provocatively named paper called Dreams Imply Programs, right? And it's always funny to read some of these AI papers from this age, because just the gap between the ambition and what the systems are able to realize is so enormous. But it was still a very compelling thing, right? And their notion is, hey, we can take specifications and essentially, through the application of deduction rules, manipulate them and massage them to turn them into implementations. And they showed some very compelling examples of how you could do this. And for many years, when you talked about program synthesis, the assumption was logical, full formal specifications describing in full every detail of the program and how it's supposed to work. And then a deductive system that, through the application of deductive rules, is going to turn these very, very high-level specification into an implementation. This unfortunately had the dual problem of both being very hard to do. It turns out the space of possible deductive rules that you can apply to get to an implementation can be quite large, and it's actually a very hard search problem. But in addition to being very hard, it was also extremely unappealing in that, rather than writing just the code in the language you know and love and that you know how to debug and you've been working for many years, now all of a sudden you have to express everything in these extremely precise, very mathematical notation and specify every single aspect of your implementation in this very, very formal way that for many applications is just really, really difficult. That really limited the appeal of these kind of techniques for a long time. Project that came out of MIT. Also a while back, where they actually looked at this problem and said, look, generating code from scratch from very high-level formal specifications is difficult, but also not super appealing. What if instead we have a system that is just there to support the programmer and to help as you go, to help with the tricky low-level aspects of coding, and I think in some ways that is the view that is winning out within the program synthesis community, right? Less about I'm just going to tell you at a high level what my program needs to do, and poof, out is going to come the code, and more about how can a system provide support to developers as they are writing code.
It is challenging, right? If you were able to give a formal description of what you want the code to do, then oftentimes it can be maybe easy then to come up with the code once you have the formal description, right? Because it takes a lot of effort to come up with the formal description.
And I think especially the failure modes of formal specifications are very different from the failure modes of, let's say, imperative programs. And this is why formal descriptions can be great at catching bugs, because you're likely to make different bugs when writing the formal description than the bugs that you make when writing the code. And so at least you can catch those inconsistencies. And sometimes you debug the code, sometimes you debug the specification. But one of the things that you have when you're writing imperative code, oftentimes getting the common case to work is actually easy. Right. And a lot of times the problems and the trickiness come in dealing with the corner cases and dealing with, forgetting to deal with some corner cases. By contrast, when you're going from a very, very declarative specification, it's very easy to end up with a system that feels almost adversarial. that you say, oh, I want the output to have this and this and this property. And it comes up with something where the output has exactly the properties that you wanted, but that does just completely the wrong thing. That is not what you wanted at all. And then you have to say, oh, no, that there is this other property that I didn't realize that I had to specify that I have to tell you about. The canonical example of this is sorting, right? If you take somebody off the street and you say, hey, what properties should sorting have? Well, the elements should come out in order, right? And that's very obvious and clear, and you can write it very easily. And then it turns out that you can achieve that property if you take your input array and you return a singleton array, right, with only the first element, right? And sure, it's in order, but that's because it dropped all but one of the elements, right? And all of a sudden, as soon as you have to say, well, no, but every element that was in the input also has to be in the output. Well, now how do you say that in logic, right? It turns out, actually, it's kind of tricky to express that property. The property about order is very easy to express. The property about making sure that your algorithm is a permutation, it requires a little bit more thought. And if you don't specify it, it's not just that you're going to get something that is buggy or that fails in some corner cases. You are going to get something that is quite literally garbage. It just doesn't do anything useful.
Formal methods has had sort of like symbolic AI has had revolutions, right? It's had its ups, it's had its downs, and you've come through some of these. What scholars through history, through your upcoming, kept you focused, kept you motivated, really inspired you?
That's a good question. I mean, obviously there's a lot of people who have, had a lot of impact on me at the mentoring level and at the, people like obviously my advisor, Raz Bodick, right, who was, just hugely influential in terms of defining the early stages of this line of work. In some ways, the community as a whole, I think sort of the right combination of open to ideas, but at the same time very rigorous about, really demanding that things be proven to a certain level of rigor in terms of really pushing to move some of these ideas beyond just the look mom no hands stage where it kind of works until you try to push it a little bit harder and then you break your teeth.
What about maybe more of a historical level, like older scholars in like the 40s and 50s or earlier in the 20th century?
It's hard to say. I think obviously we owe a huge debt to the founders of the field, and a lot of the techniques that this research built upon have their roots in very, very early work. I sometimes find it surprising that even techniques that are very popular and feel very fresh in, let's say, the programming languages world, actually, date back from much earlier than you'd have imagined, right? For example, one of the techniques that is becoming kind of a workhorse in the synthesis world is E-graph matching, right? Which the roots of this idea go all the way back to Tarjan. And so, but I don't know that I could say, oh yeah, like I want to be like that guy, or it hasn't really been sort of my way of engaging with the history and with the community.
You have this personal desire, right? This personal drive, I think that really pushes you.
Yeah, I think for me, it's a lot of it is about partly curiosity, just trying to see what will happen, and things that sound crazy, and trying to see if we can actually make them work. And part of it is about technologies that I'd actually like to use. I love programming and I love coding, and so a big part of that is thinking in terms of ideas and techniques that would actually make a difference for somebody like me.
Thanks for listening. If you are enjoying the episode and would like to support this as an educational resource, please consider giving us a like, subscribe, comment, or review on whichever platform you are consuming the show. We are just getting started, and a little goes a long way in helping us cover costs.
So you're perhaps most well known for, program synthesis and your tool Sketch. Can you give a little bit of a history of this tool and maybe lay out a bit of a basis of the foundational ideas behind it?
So when we started working in this space, we had this idea of allowing the programmer to separately say, here's what I want the tool to do, and to be able to say that in a way that is very programmer friendly. We really like the idea, for example, of using reference implementations, simplified reference implementations as a form of specification. We thought it was a much better way compared to logical specifications. But then we wanted to be able to write most of the implementation, leave unspecified some parts that we wanted the system to help, and essentially search for those missing details, or try to infer those missing details. So our first attempt of this was actually a system called StreamBit that was focused on a super narrow domain of a particular kind of bit streaming applications. And the domain that this tool was able to handle was so narrow that I think our paper had 3 benchmarks. And I spent a month looking for a 4th program that I could implement in the system, and I just couldn't find one. It was that narrow, but it demonstrated some of these ideas.
At least you need less resources with only 3 benchmarks, right? You don't need AWS credits.
No, not at all. Although we really nailed down those benchmarks. We actually showed that we could beat handwritten high-performance implementations and generate code for many different machines with different bit widths. But
what did these benchmarks look like, by the way? Were they short, simple programs, or were they interesting?
Our flagship benchmark was DES, which was the encryption standard that came before AES. And a big part of DES was these bit level manipulations. In particular, they had this bit permutations where, some part of the cipher was just, take bit number 15 and put it in this position, and take this bit and put it in this position. And so it was the sort of thing that it's very easy to describe at the high level. Oh, this bit should go here, and this bit should go here, and this bit should go here. But it's actually quite hard to implement efficiently. Our running example in the paper was just drop every 3rd bit in a string, right? Which again sounds trivial, but it's actually really hard to implement very efficiently, because if you do it naively, then you basically are running a bunch of instructions per bit in the stream, and you're not taking advantage of word level parallelism, and so you can get order of magnitudes faster code if you do clever things.
So we have an encryption scheme, and the tool sort of fills in a missing part of the code. What part of the code did it
Well,
fill
so
in?
the idea there was that for many of these permutations, you could decompose them in ways that allow them to implement each of the steps in this permutation with word level instructions, and take advantage of word level parallelism to make it run much, much, much faster, especially if you have a 64-bit machine, or if you have a machine with special instructions that allow you to do bit operations at, let's say, 128-bit parallelism. And so essentially the idea is, well, you know that end to end, you know what the permutation it is that you're trying to accomplish. And so when you're decomposing it, it was relatively easy to say, well, I know what I want the first part of these decomposition to look like. And then it's easy for the system to solve for what the second part of the decomposition should look like. Or you can have things where you can tell it that maybe for the first part of the decomposition, I know that some bits are going to shift by some amount and some bits are going to shift by a different amount. But you wanted to figure out, okay, exactly what bits should shift by how much in generating the implementation. And so these were the sort of low-level details that we could discover using a very, very specialized search procedure, just specifically designed for this. I mean, the paper was sort of a Rube Goldberg kind of thing, where it was, actually incredibly sophisticated in service of a, arguably not so high impact task. Although, to be fair, ciphers are a pretty big and important domain. And when you really, the set of applications that really need this kind of bit level manipulation of strings is small, but when you need it, you need it. And the kind of performance differences that you can get if you do it right versus if you don't can be enormous.
Can you maybe give some intuition on how these tools even work? Like a bit of a sketch of the algorithm, if you will.
So fundamentally, it's a search problem, right? You have these partial implementation, you have these unknowns. And so what you're looking for is you're searching for how to fill in these unknowns. And so for this very first paper, we had a very domain-specific search procedure that essentially decomposed these into sequences of linear algebra problems, essentially, and solved them that way. After we wrote this paper, and I said, I spent a long time looking for other benchmarks that could be implemented and used in the same procedure and was unsuccessful. Sanjit Seshia came to interview at Berkeley before he became a faculty member. And so I didn't actually go to his interview talk, but Raz did and said, hey, do you think he talked about these things called SMT solvers, and they can reason about bit vectors. Do you think we could use them for addressing this search problem? And so we started looking into this. We started collaborating with Sanjit, thinking about how we could reduce these search problems into SAT or SMT problems. And what became very clear very quickly was that you couldn't quite use the solver directly, because in the problem that you needed to solve for synthesis, there was this quantifier alternation, right? You're looking for a program or a completion of the unknowns that is correct for all inputs, not just for one input. And so basically the three of us started brainstorming, and we came up with this idea of, well, what if we focus on concrete inputs? And if you're looking for something that only works for a concrete input, then you don't have to deal with the quantifier alternation. And maybe if we do that a few times, you can actually find the solution that generalizes beyond the small number of examples where you tried it out. And these were really the key ingredients in Sketch, the use of a SAT solver to solve the search problem. So you can frame the search problem as a giant Boolean formula for which you're looking for a satisfying assignment. And then the use of counterexample-guided, we called it counterexample-guided inductive synthesis. The idea was, rather than try to solve the problem for all inputs in one shot, try to solve the problem for a small number of inputs, and then checking whether the solution generalizes to all inputs. And if it doesn't, then get a counterexample that shows you where it fails and add that as a new input for which you're trying to search. And so that was really the basic idea behind the synthesis algorithm that is used in Sketch.
So this idea of a counterexample to sort of guide the search and refine the search, this seems to be coming up in several domains, right? Why is this such a powerful idea?
This is a really good question. I think, when we started working on this, it was just a very pragmatic decision. Hey, we have this solver that is really fast, but cannot solve problems with extra quantification. And there was this notion that, hey, oftentimes just a small number of examples can actually give you all the information that you need about how the program should look like. Generally, if you have a few examples that run through the common case and you make sure that you have examples that cover all the corner cases, you're good. And so, but in the beginning, it was just a very pragmatic decision of basically managing to take our problem statement and squeeze it into the solver that we had available to us. But it has turned out to actually be a much more general idea that has proven to be very, very useful in lots of other contexts. Within the verification world, there had already been a lot of work by that time on counterexample-guided abstraction refinement, and essentially looking at the failures of a verifier and using those failures to refine it to help you. But in the synthesis case, I feel that the intuition behind it is much stronger, because there is this very strong sense that learning from examples is a thing that we know how to do. And oftentimes it's much easier to reason in terms of a concrete case where we can see exactly what's going to happen in that concrete case, compared to thinking about something very abstract. And so having an algorithm that directly leverages those counterexamples has turned out to be really, really powerful, even in the context of different strategies that use different kind of solving or searching techniques to find programs, or looking for programs that work for particular concrete examples just dramatically simplifies the problem.
This analog of a conflict or a counterexample, it appears everywhere, even outside of verification. Like in verification, we have like conflict learning. Recently in machine learning, a very popular idea is like adversarial examples. If we can find where we're wrong, we can now train on where we're wrong. Even philosophically, right? Like it's a big deal to try to find counterexamples to ideologies. Or even in math, right? Finding paradoxes. It's a very powerful idea.
Yeah, this idea of learning from your mistakes is a really powerful thing.
How hard are we pushing this in these tools? Can we push it more? Can we be more efficient with it?
That's a good question. One of the things that is sort of a central question in a lot of these counterexample-driven algorithms is, what is a counterexample, right? And it turns out the different ways of representing a counterexample can give you vastly different powers of elimination. So a really good example for us, and something that was really eye-opening, was when we started dealing with concurrent programs and applying this counterexample-guided inductive synthesis idea as to concurrent programs. So one way of doing this, and what we initially tried, was to essentially think of the concurrent program as just a sequential program that takes the separate input called a schedule that essentially tells it, okay, first run this thread for this many time steps, and then this thread for this many time steps, and then this thread for this many time steps, and then this thread for this many time steps. Now, if you do that, then this is just a sequential program, right? It takes as input the schedule and just runs instructions from every thread according to the schedule. And if you give me a wrong program, right, a program that has a bug, I can give it to a verifier and get a schedule that says, or give it to a model checker and get a schedule that says, yeah, if you run, this many steps on this thread, and this many steps on this thread, and this many steps on this thread, and this many steps on this thread, you fail. Well, the problem with doing it like that is that counterexample, if you represent it that way, it's very brittle, right? All it takes is for the synthesizer to insert an instruction somewhere. And all of a sudden, that schedule that was exposing that bug in that program, because now it's offset by 1, it's switching threads at a slightly different time than the original program. And maybe now it doesn't fail. It doesn't mean that you actually fixed the problem that was being exposed by the previous schedule. All it means is that you made this completely irrelevant cosmetic change to the program, but it changed how the schedule gets interpreted, because now there's this one extra instruction, everything is out of line, and it makes it look like this schedule is no longer failing, even though you didn't actually fix anything in the program. And so having the right representation of these counterexamples so that you actually learn the right lesson from the counterexample is extremely important. Otherwise, it's very, very easy to learn the wrong lesson from the counterexample. And sure, the exact same problem will never happen again after you do the fix, but you might end up with what is essentially the same problem, just manifesting slightly differently.
It's interesting. All counterexamples are not created equal, right? Sometimes you find like maybe an edge case or something that's not super, maybe semantically interesting, or depending on the application. How do we try to find what a good counterexample is? Something that can really prune these extremely large search spaces. How do we quantify this?
That's a good question. And I think part of the problem of giving a straight answer to that is that it can be very domain specific, right? Depending on the domain, there are particular aspects of the example that are the ones that you really, really want to highlight, and you really want to hone in on them to make sure that you actually get that you're actually learning the right lessons from that counterexample.
A bit back to synthesis. What are sort of the biggest engineering challenges and the more recent developments in these tools in the last few years?
I think there's a couple of things. One is, I think as a community, we've done a really good job of building a pretty solid body of work such that if you have your own synthesis problem and you want to attack that synthesis problem, you can, based on the research and the literature, you can have a pretty good idea of what kind of strategies work or is not going to work and how to implement your own synthesizer to go and solve your problem. But there is no synthesis equivalent of PyTorch, for example, of sort of a general infrastructure that allows you to easily implement these kind of solution, and it gives you portable performance across a variety of platforms that allows you to leverage high-end hardware when it's available from the same problem description. We really don't have that. And so what it means is that it's difficult for people who are not, PhD students or PhD graduates in the field to leverage some of these techniques to attack their own problems. Probably the closest thing we have to this kind of infrastructure are things like Rosette out of Amina Torlak's group at Washington. Sketch kind of tries to be a general tool that people can apply to different problems. But by and large, what you find is that you can often do much, much better by writing, essentially rolling your own and writing a specialized solution for your problem domain, which is certainly not something that you see in deep learning, for example, right? You're just going to be much better off using one of the established platforms because there's so much engineering that has gone into that.
What are some of the most pragmatic applications of these technologies right now?
So I think one that has gained a lot of traction is data wrangling.
What is that?
So this is a problem where you have data and you're trying to, usually in the form of text data, and you're trying to manipulate it in some way as a prelude for actually either using it for learning or using it for some kind of data mining or even just organizing it into a database, for example. Right? But this kind of text data transformations that can sometimes be pretty involved, and often are required to be done by people who might not be software engineers or even computer scientists, right? This might be statisticians or domain experts of some kind that just have their data in a giant log file or in a giant text file, and they need to organize it and order it and make it put in a format that downstream tools can use. So for this kind of problems, programming by example has proven to be very, very effective. And this is an area where you can really show a lot of value from automation.
What about perhaps some current surprising applications? I know you have this great linguistics example I saw online.
Yeah, so we're actually really excited about these applications to program synthesis in domains outside of sort of traditional programming. Yeah, this linguistics was actually a cool example. This was work that was led by my former student, Kevin Ellis, and in collaboration with Josh Tenenbaum and Tim O'Donnell, where we showed that we could leverage program synthesis to take collections of words from a language and automatically derive morphophonology rules that explain essentially the mechanics of the language.
What is a morphology?
So you have two kinds of rules in linguistics. So one is a morphology rule. So think of, for example, the rule that tells you how to construct the past tense of a verb by taking the stem and then adding ed at the end, right? So climb becomes climbed. And so that's a morphology rule that tells you how to do that. And then you have phonology rules that tell you how within a word certain sounds change based on the context, right? So an example would be the past tense of walk. So there's a morphology rule that says, well, it's walked, where you have a D at the end. But when you say walk, you say walked. You don't say walked, right? So it's like a T sound at the end rather than a D sound at the end, right? And it turns out that there's a rule that explains why you have to modify that sound at the end to be this hard T, like walked, instead of this softer D, like walked, right? And so that's a phonology rule.
And these rules are it's almost syntactical, right? It's almost odd how logical they look.
Yeah, I mean, one of the things that made this a really interesting and exciting domain is that the linguists over the span of decades have developed very, very good formalisms for describing the both morphology and phonology rules. And so these formalisms give you a basis from which to do program synthesis, right? Because now the synthesizer is not trying to just discover from scratch how language works. Instead, it has this background theory that is given by these formalisms used by linguists. And so all it has to do is discover rules in terms of these formalisms. And this is really the big difference between the synthesis approach and a more traditional machine learning approach, which is that you can provide as input this vocabulary that then all your rules and all your programs are built from this vocabulary. And that gives you an enormous power to give background knowledge to the synthesizer. Another application domain that we're very, very excited about is computer-aided design, CAD.
Oh.
So most CAD systems have essentially a little programming language under the covers that is describing all the shapes and all the manipulations that you can do on those shapes. And so it turns out if you have the ability to do program synthesis over that language, there's a number of really exciting things that you can do, both at the level of individual mechanical parts as well as at the level of assemblies, bringing together many different parts.
When we try to find applications, it's often a little bit intimidating, right? Like, will synthesis even work on this application? And the complexity of what synthesis is doing is tremendous. It's a very hard problem from a complexity theory standpoint. What sort of problem characteristics indicate that synthesis could be very useful here?
I think a really big one is that you have an established vocabulary and an established body of prior knowledge that you can build upon to construct your programs, right?
Can you make that more concrete?
Well, so for example, I think it's useful to illustrate it by counterexample. So vision, for example, is one domain where I don't think we have that kind of vocabulary, right? If you think about, how we perceive that a dog is a dog, there's not a very good sort of underlying set of primitives that you can think of the program for recognizing a dog as being a composition of these primitives, right? Where you have a good vocabulary for describing how to construct this program, right? That's a dog because it looks like other dogs that I've seen in the past.
It's more of a pattern recognition problem, right, than a deductive problem.
Yeah. But you can have pattern recognition problems for which, nevertheless, you have an underlying vocabulary that allows you to describe those patterns very effectively, right? So, for example, many of these data wrangling problems are also pattern recognition problems, but there are underlying concepts like regular expressions, for example, that give you a pretty powerful vocabulary for describing the sort of things that you're going to be looking for. So you can use that as a basis for synthesis, right? I think one of the problems in the context of images is that we don't really have the image equivalent of regular expressions.
We talked about this a little bit. Synthesis is so interesting because it combines these two, like it has applications to both machine learning and pattern recognition, as well as these deductive techniques. And both of these techniques, they seem to really need each other, right? Like if you look at these pattern recognition systems, when you look at how they work, how they function, it's kind of natural to become skeptical if it actually understands what it's doing. It doesn't seem to be that deductive reasoning. On the other side of things, we have these deductive tools, but they're solving these very hard search space problems. And there's this neurosymbolic idea that relates to synthesis, and it's another area you're working on. What is sort of the history of this field? It wasn't just, it seems like it's re-emerging now, but it has a longer history to it, right? Where does it come from? Why do we need it? And why is it sort of re-emerging?
I mean, I think in terms of where it's coming from, I think one of the things that is actually exciting is that you have people who are coming at this space of solutions from many different backgrounds, right?
Yeah.
And on the one hand, you have people who have been experimenting with language models, and particularly the NLP community is one that has traditionally had to deal with this interaction between symbols and neural representations, right? At one level, language is entirely symbolic, and yet at another level, it's there's an enormous amount of scope for optimization-based techniques, and in fact, purely symbolic approaches to language, by and large, tended not to work very well, because they couldn't really deal with all the messiness of and all the ambiguity in real language, and all the way in which contextual cues play a role in natural language. And so you do have a subset of the community that is very much coming from the NLP side, and some of that experience of using neural networks to deal with symbols and bringing that to bear into other kinds of problems. And then you have people like us who are really coming more from the purely symbolic world, and that experience of working with code where, in some sense, code was the last refuge of the original first wave of AI, right? A lot of those logic-based techniques that were kind of abandoned when it came to problems of common sense reasoning and sort of the original AI agenda turned out to actually be really, really useful when you're trying to reason about code, where everything is more well-defined and precision is actually a quality that you care about. And so I think the kind of ideas and the kind of techniques that we bring to the table are very different from the kind of techniques that, say, people from the language world are bringing to the table. But it's been really exciting to see now that conversation starting to happen between these different subfields and people who are coming from different directions.
It's a bit of a holy grail, right? Like, to combine these two sort of paradigms of AI. What are sort of the next steps you think right now to get this really going, to get like really powerful tools and applications?
I think there's a couple of things.
And even a theory. We almost have no theory on this topic. What are the next steps to make research progress?
Well, I think there are a lot of steps, certainly algorithmic, right? We need better algorithms for how to attack this combined neural and symbolic problems. I think we also need to, when we talk about neurosymbolic, you're really talking about a whole space of combinations and a whole space of approaches, and knowing exactly what points in that space lend themselves better to different kind of problems, and what characteristic of a problem make it more amenable for one kind or another kind. And then there's the performance question. For a lot of these things, performance really, really matters. And getting a big leap in performance, once you start talking orders of magnitude, it starts becoming a really qualitative difference. The kind of problems that you can attack and the kind of solutions that you can get changes very dramatically.
I like a theoretical level. When we try to glue these tools together, literally, it seems it's very difficult. It seems like we don't have the right abstraction yet. Do you share this thought, intuition, or like what's your vision?
I think one of the things, for example, that in some ways with deep learning, I would say we got lucky in the sense that you're solving an optimization problem that we really had no right to expect that it would be solvable. right? It's a really, really hard 10 years ago or 20 years ago for sure. If you had told people that you would be solving optimization problems in a billion dimensions, that would just not have sounded reasonable, right? And yet here we are.
And this phenomena repeats. This phenomena repeats, right? It repeats over several domains, not just deep learning, but also in automated reasoning. Worst case complexities. If you have like just n equals 100, we quickly get beyond the number of particles in the universe, right? But it can solve these problems in a second.
Yeah. I mean, we can
like a solver.
It's the same with SAT, right? We're solving SAT problems that we really had no right to expect that we would ever be able to solve them, right? And partly it's the nature of these problems. But now all of a sudden we're being asked to solve combinations of the two, right? And all of a sudden you find that, for example, when you're trying to incorporate more program structure into neural networks, all of a sudden those problems that worked fine before, now all of a sudden the derivatives start getting nasty. And all of a sudden you start getting local minima again. I think part of the issue is we have these two classes of technologies that individually we already don't quite understand really well why they work at all. And now we're having to figure out why their combination doesn't work so well, or how to make their combination work better. And so it is a challenging problem.
Do you have any intuition on why we can do this at all?
In the SAT case or in the neural case?
Could it be a common intuition, or are they disjoint?
I would be surprised if there was some underlying commonality between the two of them. I think in the neural case, I can't say much more than sort of the conventional wisdom that once you get to these higher dimensions, the dimensionality is actually helping you not have not run into local minima. That, I think in many cases it boils down to the fact that the kind of problems that we care about turn out to be much simpler than the worst case that you can get with any of these kind of techniques.
So we talked about this previously. Software engineering is actually quickly growing as one of the most common jobs in all of North America. In several states, it's already the most common job. And based off of how many people are learning programming and how many students are entering computer science, I wouldn't be surprised at all if it becomes more dominantly the most popular job in the next several years. However, there seems to be this growing momentum to automate away parts of the industry, whether it's through just automatic programming, better developer techniques, better practices. It's possible that there's this huge push for jobs from the people, but maybe this technology will take away some of the jobs. Do you have any thoughts on the socio-economic impacts of such a potentially quick rise and fall from a single profession?
Well, I mean, I think the modern civilization runs on software, right? Almost every industry that you look into and you ask, why are things not better? The bottleneck is usually software, right? How are we going to make our cars more efficient? Software, right? How are we going to make our airplanes more efficient? Software. How are we going to make our power grid work better? Software, right? Our ability to write software is, one of the key bottlenecks in the progress of civilization these days. And so anything that we can do to make that process work better, to allow us to create more reliable software more efficiently with less work, I think it's going to take us a long way towards addressing a lot of problems that we have to deal with as a society, right? I mean, of course, not all of them, and this shouldn't be interpreted as saying that all our problems in society are technological or have technological solutions. But certainly those that do, a big challenge is software, right? And our ability to write software quickly and reliably. And, if you think about machine learning today is way more powerful and, in many ways much easier to use than it was, before this latest deep learning revolution, right? It used to be that that you really needed an expert to do very careful tuning and feature engineering if you wanted to get any kind of machine learning to work, right? Nowadays, a lot of the feature engineering is no longer as important or as necessary. The techniques that we have kind of reduce the need for very careful, detailed feature engineering. You can just do hyperparameter tuning so that you don't need so much expertise to figure out exactly what the right set of parameter is, right? And did that make machine learning experts less necessary or less in demand? No, quite the contrary, right? Now, all of a sudden, everybody wants one because the sort of things that they're able to do and the kind of value that they can bring to an organization went dramatically up. I don't see why it should be different with software. If programmers can be more productive and they can generate better code at higher quality in less time, it all of a sudden they become less valuable. Now, it's true that a lot of this depends on how these techniques develop, right? So, for example, techniques that allow skilled programmers to do more efficiently are going to have a different impact from techniques that allow unskilled people to do things.
In the worst case scenarios, perhaps this won't be super impactful, or even in the medium, in the worst case research progress scenarios or medium case research progress scenarios, this might not be super detrimental to the industry. But say we have a very positive, say research goes really well. I've heard some people say that testing might go away if these symbolic techniques and correct programming really go off, right? Large chunks of tech companies, the need for those jobs might disappear. And we're quickly training people for those jobs. Do you ever think about this?
Well, it's certainly true that the nature of programming is likely to change. I think actually, software developers are in many ways, I think, much more prepared for this sort of change than people in any other industry, in that the rate of obsolescence of many programming tools is already quite high, right? I think much more than in any other industry. People in software know that the only constant is change. Tools are changing all the time. The preferred frameworks and infrastructures that people need is changing all the time. And, yes, there are a few people who can, work as COBOL programmers and make that their niche. But by and large, I think the industry is much more used to a very high pace of change compared to other industries. So, yes, it's, maybe we won't have testers, right? I don't think anybody goes into software engineering or into computer scientists wanting to be a tester. I might be wrong, but it's just one particular task that is part of the software development process today, where we might need now different kind of experts, right? Maybe the tester is no longer going to be the person writing test harnesses. It's now going to be the person who is having to dig deeper into, maybe know a lot more about formal methods, for example. to really be able to tailor the automated code analysis solutions to a particular platform.
It's interesting you use the phrase like next generation of software, because people often consider this to be machine learning right now. There was this paper circulating around recently calling machine learning software 2.0, and Elon Musk endorsed it on a podcast. It's not rigorous yet, though, right? It doesn't feel complete. But it seems like if we could combine these technologies, maybe we'll get software 3.0. What would that look like?
Well, I think...
Or is that not even the right way to think about it?
That is one of the big questions in the field, which is how do we leverage some of these things that we're learning how to do and some of these new capabilities that we have and really incorporate them into a development model, right? When I look at Copilot, for example, on the one hand, I see an incredibly impressive system, right? That is capturing an enormous amount of knowledge about software and is able to deploy it in a really interesting way. And yet, as a tool, it really doesn't feel like the right way to deploy these capabilities, right? This notion that you're going to just keep programming the same way you were going to program before, and sometimes it's going to suggest extra code that maybe if you're lucky, it'll happen to be exactly what you wanted, but maybe not, right? It just doesn't feel like the right way of deploying these capabilities. And, yes, in some ways it addresses the code search problem or the, Google things, look at them up in Stack Overflow problem, but it doesn't feel like it's the thing that is going to dramatically transform programmer productivity. And at some level, to have this immense knowledge store of code and just deploy it to give you, bad suggestions and wrong code completions, it doesn't seem like that is the best use of those techniques. But what is the best use of those techniques, right? And given that there is this capability and given that you can do this, how could you rethink a software development environment? How could you rethink a programming language or a software engineering methodology to leverage this incredible amount of knowledge that's stored in these models? We don't know.
Changing gears a little bit. We don't use this term a lot in computer science, but there's this idea of replication that keeps appearing. Like now we're getting AI to teach itself math. We're getting AI to learn how to program itself, maybe learn how to program computers. And this is starting to feel like, self-replication a little bit. It's almost like a sci-fi movie, right? Like it seems like perhaps a lot could happen once, machines begin to program themselves, begin to self-replicate. Do you have any thoughts or fears or ambitions for AI and self-replication?
So, by the way, when you said replication, I originally thought you were going to ask about sort of scientific replication. But I know what you're talking about, right? And there is sort of this latent fear of the potential for setting up an exponential process, right? Exponential processes tend to be hard to control once when they get going. And as soon as you have a feedback loop where things can build on itself, you have the potential for this exponential process, right? And so, in particular, when you have code that is writing itself and that is helping improve itself, there is this potential for on the one hand, a virtuous cycle, right? Where better tools lead to better tools, lead to better tools. And, I think one of the things to, it's kind of a truism that, if something cannot go on forever, it won't. And, I think sometimes it's easy to forget these things. In nature, there really aren't true exponential curves, right? What you have are sigmoids. Yes, there is an exponential growth. Yes, things start feeding into itself. But sooner or later, you have, countervailing process that, you start reaching the limits of whatever is the underlying thing. And things plateau, right? And generally, we like to talk about bacteria, for example, like reproducing exponentially. And yes, they reproduce exponentially, but there's a reason why the world is not just one giant bacterial colony, because yes, they grow exponentially until they can't, and then they don't.
There's still constraints somewhere, right?
Yeah, exactly. And so I think really the interesting questions is what are going to be the constraints, and what are the fundamental limits that keep this process from going on forever. I think it's an interesting and exciting question, right? I think under this there's also the sort of this underlying fear of technology that we can't really control. And I think that has less to do with, the exponential growth itself, and more of just a social decision of how much control we give machines over society, right? And you don't need a Terminator scenario to, for things to go really, really wrong, right? Exactly, it doesn't have to be AI. It could be, malicious state actors hacking into systems. It could be, I think there is an inherent risk when we rely on technology for essential aspects of daily life. And we have to make sure that when we build systems around technology, that we actually think hard and carefully about, what happens when things malfunction, what happens when the technology breaks, what happens when, any of the number of things that can get technology to not do what it's supposed to do are inevitably happen. How do we make sure that that's not just going to bring society down with it?
Yeah, you're right. We often think of AGI, right? That's sort of the technology that will doom us. I think self-replication could be one. And this effect, as you were sort of alluding to, can snowball, right? Like once we get a machine that can consistently begin to improve on itself, like things could get out of control. But we're not close to that yet, right? There's still a few steps. But it seems like we're getting closer, right? It seems like we're getting closer to this ability to create machines that can program themselves, machines that can learn math by themselves. When should we start having alarm bells going off?
I feel like we are at the stage where there are a lot of really important social questions around how we deploy technology, how we rely on it, the extent to which we allow technology to drive daily life, that have nothing to do with, Skynet, and that are actually extremely pressing and important to engage in. And so I kind of worry that worrying too much about the what if the machine becomes sentient and then decides it doesn't like us, can actually blind us into, the very immediate and very real dangers of carelessly deploying technology. And now some people would argue that, yes, maybe the probability is low, but sometimes it pays off to worry about low probability things, because low probability things sometimes still do happen. But I also think that the things that we need to do as a society to address many of these much more immediate questions about the impact of technology on our lives are things that ultimately are about making society more resilient to technology malfunctioning or misbehaving, right? In a way that, even if you really do think that smart machines are the big threat that we have to worry about, I think is still helpful, right? To address some of those issues of, how computer systems malfunction, regardless of whether it's just a bug or whether it's, a sentient computer explicitly trying to do you harm, right? At some level, is it really that different whether it's just the computer having a bad day and deciding it doesn't like you, or whether it's a malicious state actor hacked your computer and is getting it to do something bad, right? It doesn't really matter what the difference is.
There feels like there's this urgency. These autonomous programming things that are getting really good, right? And recently there was a Google engineer who claimed there was some sentient system over there. There are societal things that we need to do, right? And there seems to be urgency, right? We need to get ready for this technology that might come. What are the next steps at a societal level we should be doing?
I mean, I don't think we do. And I think this is the fundamental thing, right? I don't think this is the biggest thing that we should worry about. I don't think our language models are sentient. I really don't think it's very productive to be worrying about that.
That's fair, yeah.
We don't even know how to define what it would mean for the machine to be sentient, right?
Yep.
How do I even know that you're sentient and that you're not just faking it, right? It's
a lot of people think the description of the whole universe can fit on a single T-shirt, right? Everything might be deterministic.
So I feel that worrying about that kind of issue is just not very productive. I think we're much better off taking a much more pragmatic and practical approach to this and looking at really how is technology being deployed? What are the social impacts of those deployments? And are we building systems that are too reliant on technology working in just the right way and that are going to create major social havoc when it doesn't? Are we substituting, democratic control for, very particular policy choices disguised as algorithms? Those are some really serious questions that are independent of the question of whether the machine is sentient or not, right? If power goes out across the East Coast because of a computer malfunction, does it really matter whether it malfunctioned because it was sentient and it decided that it didn't like me, or whether it just malfunctioned because it had a bug and it broke? Who cares, right? The real question is, should we have a system where computer malfunction can take down half the power grid?
Changing gears a little bit, I like to ask people, because I have a very opinionated answer to this question. What is the most important invention humans have ever made? I personally think it's language, the ability to transmit information. And computers have given us this mechanical way to deal with information. And you're a programming language guy and an AI guy and many things. But this idea of language, it seems like it's sort of really being pushed right now in research. We have these language models. There's a lot of papers right now in the neurosymbolic area talking about how to incorporate ideas of language into AI. Where does language fit in like this taxonomy of reasoning that we have?
So by the way, I do agree with you that I think language is certainly right up there as the most important invention. And
do you have another one that it's up there, but is it number one for you?
Well, I mean, I think the writing is right up there. It's
that's true. Yeah.
It's hard to write if you don't have a language to write in. So that's certainly, I think from that perspective, you could say language is very important. I think both language and writing have something in common, which is that they allow the brain to use resources outside of itself to think, right? All of a sudden, once you have language, your brain can leverage the whole community to making decisions and to arriving at decisions. It's like the difference between a single computer and a network of computers. That's what language gives you. And then with writing, all of a sudden it gives you the possibility of a mechanical aid to thinking, right? The fact that you all of a sudden have infinite memory that can even span generations, right? And that I can leverage the fact that I can learn from things that people 2,000 years before me wrote, and it makes sense, and I can build on that is huge. Now, in some sense, computers, that has been one of their defining characteristics, right? Even before, we were talking about language models, right? This ability to represent things symbolically and store those symbols and manipulate them later. That's one of the things that makes computers so powerful. I think in the context of AI, one of the things that we are seeing, and that is kind of exciting, is that all of a sudden we can use text and human interpretable text as sort of this lingua franca to represent all sorts of different problems, right? And to me, it's really fascinating, this idea that, the same kind of underlying architectures, and in some cases, even the same models that you can use to, write English or write prose, that you can use them to write code. You can reduce all sorts of math problems and all sorts of different problems down to this uniform text-based representation and process them with the same architecture. I think it's really fascinating, and it opens a lot of possibilities.
We talk about these multiple techniques for AI a lot. The machine learning, abductive, inductive techniques, they seem really good at finding these continuous representations, almost like a mental state. But it's hard to communicate that with the deductive side of things. The deductive side, we have these nice symbolic equations, and we can do great things with this, but it's hard to go back to that continuous state, as you were mentioning. However, though, when I do my own reasoning, me as a person, when I want to communicate my reasonings, I do both of these styles of reasoning, these abductive, inductive pattern recognitions in my daily life, and I also do deductive reasoning in my daily life. But when I try to communicate it, I have to use language. And language is a bit of a tool for me to say these things. I'm able to say both these deductive ideas as well as these abductive, inductive ideas. And I think because of this, there's a bit of a push in research, and especially like AGI research, to incorporate both language and to sort of act like a glue between these two technologies, these like automated reasoning, like solvers, programming ideas, as well as to these pattern recognition ideas. Do you think there's potential in this? Is this the way to think about it, or do you have any thoughts? Language seems like this sort of tool that we humans use to combine deductive reasoning with abductive reasoning. This is something we haven't quite gotten computers to do yet. We haven't figured out how to leverage computational language to sort of mix together deductive reasoning and abductive reasoning. Is this a hard problem philosophically, empirically? Is this even worth considering?
Language is a pretty strong basis for combining these two kinds of reasoning. And, we see this nowadays in some of the work that is going on around some of these big language models. The fact that you can take the output of this model and then reason about it following formal rules, right? Whether you're doing program synthesis, generating code from a language model, but then you're taking that code and you're running program analysis on top of it to be able to check it or even run program analysis as you're generating it to help guide what you generate, right? That's already an example of applying formal rules over the output of this program. People have done similar things in the NLP side, being able to, as you're spitting out a sentence, run grammar checks, for example, to make sure that what you're generating is grammatically correct, say, right? This is one way in which you can combine these two different modes of reasoning.
We have this sort of pipe dream to have this nice, elegant combination of these two, right? Is this possible even?
Well, I certainly hope it is, right? I think that is the big question for our research field, right? How to do this. And, at some level, we have an existence proof of a, most early analog device that nevertheless manages to represent symbols and manipulate them. And so, there's I don't think there's a fundamental incompatibility between them. We just need to figure out how to do it.
Instead of perhaps maybe gluing them together through a feedback loop or some interface, another idea is perhaps one emerges from the other. Perhaps deductive reasoning emerges from abductive and inductive reasoning, or vice versa. Do you think this could be the case, or is it likely a feedback loop or a glue of these two?
There is, a particular position that some people in the community have that says, neural networks are all you need, right? And that whatever symbolic reasoning you think you need, we can all fold it into the neural network and have the neural network do it, right? And again, kind of the existence proof of this position as well. Brains do that, right? Brains do symbolic reasoning without necessarily having digital calculators inside of them or having built-in specialized symbolic infrastructure, right? It's all neural. But I think that position is, while I think it's interesting from a scientific perspective, it's not particularly practical, right? This notion that I'm going to use a digital computer to emulate a neural network, to emulate a digital computer, just seems awfully roundabout, right? And I think it certainly it feels like it ought to be the case that, having techniques that can leverage the computer as a computer, right? That, in the same way that, yes, my brain can do math, even though it's all neural, but it can do math way better if it has access to a digital calculator. Right. And, the kind of math that I can do purely inside my brain is actually extremely limited. Right. It's only when I extend my brain with pencil and paper, for example, and this infinite memory that pencil and paper gives me, and this ability to check my work that pencil and paper give me. It's only then that I can actually do anything non-trivial, right? The amount of math that even fairly skilled people can do entirely in their head without any kind of formal aid is actually really, really limited, right? There are things that you can only do when you have that external symbolic support, whether it's in the form of pencil and paper, or whether it's in the form of a computer or a calculator. And so I think I don't see a reason why it should be different with a neural network, right? Yes, maybe you can train it and push it to do a little bit of arithmetic, but it's never going to be as good as doing arithmetic than an actual calculator, right? Than an actual computer. And it really begs the question of, if you have a computer and you have a calculator that knows how to do arithmetic, why would you actually want to just do it in the neural space?
It's hard to see a neural network inventing calculus without having, essentially extensive training knowledge about what calculus really is to start off with.
But not only that, right? So maybe you can invent, it's fine. Maybe you do give it this knowledge and maybe it does discover calculus, right? I think the real thing that symbolic reasoning and especially the kind of symbolic reasoning that even humans cannot do without external support is not just sort of being able to take derivatives, but being able to take derivatives of huge, long expressions that we've never seen before, right? It's one thing to be able to take a derivative and, I can compute derivatives in my head, even for, medium-sized expressions. But I couldn't compute a derivative of a 10,000 or a 10 billion parameter neural network in my head, right? That just, I cannot. Nobody can, right? But I program a computer to do it, and the computer can do it, right? And, in a similar way, yes, you can probably train a neural network to do calculus, right? And to know the rules and to know. But if you don't give it access to the kind of symbolic infrastructure that allows it to really scale that reasoning arbitrarily, then, you might end up with something that knows how to do some integrals and can compute a few derivatives, but it's not going to have the kind of ability that symbolic reasoning really gives you of this arbitrary scalability and this arbitrary ability to reason even about very out of sample inputs.
We talk a little bit negatively, right, about these techniques. They do have limitations, both machine learning and symbolic techniques. But in both areas over the last decade, there's been empirical exponential progress. And that's exciting because exponential progress is very fast, right? Like that's a very good sign. Let's assume it continues to some extent. It's hard not to wonder what kind of applications might come from this. Both, from a synthesis, neurosymbolic, everything we've talked about. What sort of application that might come in the next couple decades are you perhaps most excited for? And which ones are you most fearful of, both at a personal level as well as like a society level?
Well, I think to me, one area that I'm generally very excited about is scientific discovery. All right. I think this ability to turn observations into knowledge and this ability to create an understanding of the world that allows us to, really understand how the world and the universe works is incredible. And I think this is a space where neurosymbolic techniques have a really important role to play. The ability to not just make predictions, but to generate models that actually capture our understanding of our current understanding of the world and expand on it rather than simply making black box predictions. This ability to generate models and then give us insights about what new questions to ask about how different interventions might actually affect the behavior of a particular process. I think that could really be transformative in every aspect of society, right? This ability to turbocharge scientific discovery is incredibly exciting.
And it's hard to figure out what will be, because it's automating science itself. It's hard to really infer what could happen, right? Perhaps we find something bad. Are there any sort of dystopian futures you ever think about, something that we haven't mentioned?
Well, I think there is a general risk with any kind of technology that is, that it gives a pattern of respectability to, ideas that are otherwise really bad, right? And so, there are many questions in society that really boil down to, we just have to negotiate with ourselves and agree on, anything from like, what's the right level of taxes, right? It's something that feels a little bit mundane and low level, but there's no objective measure of what's the right level of taxes, right? We as a society need to decide like what things we want to do collectively and how much money it costs to do those things. And there's disagreement. Some people think that, the government should do certain things. Some people think that it shouldn't. And, but this is a social question that, we as humans need to sit down and hash out and make a decision. There's a risk that on decisions like this, we can say, well, let's ask the machine, right? The machine is objective and the machine knows what the right answer is. Let's just go and ask the machine. And I think there is a risk that in many of these important social questions, we might just abdicate our responsibility as citizens to make these decisions and just say, well, the machine says this is the right answer, right? So that's what we're going to do. And we're not going to discuss it, and we're not, because the machine said so, right? And the machine knows everything. And, it might sound kind of funny that everybody would agree on what the level of taxes should be just because the machine says so. But, we see this happening in other spaces where sometimes a particular policy's approach is deemed as just the right one simply because it was arrived at in a particular systematic way, but without really considering all the all the interest or all the social factors that went into that were maybe unseen inputs to those models.
AI could really help with this, but it also seems like a bit of a modeling problem, right? Like, if we have a bad model to do this, to like try to achieve this sort of society, or if the person who designs the model is malicious or adversarial, this could quickly get dystopian, right?
Well, yes, but I don't think you even need a model to be adversarial or malicious for things to get dystopian, right? It's I think the dystopian aspects of it come when we take social questions or questions of values or questions that are really about our particular preferences and couch them as technical questions that somehow an algorithm is going to be able to give us an answer to, right? So you see this, for example, like in the abortion debate, where you see people arguing of somehow wanting to come up with a technical answer to the question when does life begin, right? Does it begin when you're born? Does it begin at conception? That's not a technical question, right? It's something that just as society has to decide at what point somebody is awarded sort of membership in that society. It's not a question that an algorithm can solve. It's not a question that you can somehow gather some data and settle the question. And data can inform the question. You can, but at the very fundamental level, it's a question that it's something that has to be agreed upon as a society, and not something that's just going to be resolved by a machine.
On this point, and this will be my last comment. I think maybe I'm nitpicking a little bit, but I think you might have contradicted yourself. At the beginning of the podcast, you said a lot of your drive for this field was passion and curiosity, right? Wanting to learn science. But then later, you said you hope for automatic scientific discovery. Say we hit this utopia of we're able to really make machines that can discover science, do research. If these machines really get cooking, it might not be pragmatic for humans to do science anymore.
Well, it depends on what you mean by doing science, right? If by doing science you mean standing on a lab bench and doing calculations by hand, the machines can do that, right? To me, doing science is really about posing questions, right? And gaining an understanding about the world and gaining an understanding about how things work that we didn't have before, right? Yeah. And that is a personal thing, right? The machine can do the mechanics of building these models for us, but we are the ones who are gaining this understanding, and we are the ones who are driving the questions. We are the ones that get excited when we understand, how cells work and how the universe expands. The machine can help us process this huge amounts of data and can give us models that are consistent with these things. But ultimately, it's us that are gaining this understanding, right? And I think that is the big difference between just training a model that, sure, it can make some predictions, but if it doesn't actually lead to an understanding that leads you to ask new questions, that leads you to pose different ask different questions, then you're not really advancing science.
All right, I'm out of my question sheet. If you had any other comments, or we could just end it here if you want.
No, this was great. This was a lot of fun.
Awesome. I had a great time.